Start with one database on one machine. Two users write to it, two users read from it. Whatever order the writes arrive in, that's the order they happen. Everyone who reads afterward sees the same thing, because there's only one thing to see. This system has no interesting properties. It has one machine, so it either works or it doesn't. That's the reason nobody runs it this way. One machine is one failure away from 0 machines. So we make copies. 3 copies of the data on 3 machines, ideally in 3 different buildings. Now a machine can die and the data survives. The moment you do that, you've created a new problem that did not exist before. Those 3 copies have to agree with each other, and they are not in the same place. Everything in this video comes out of that one sentence. CAP stands for consistency, availability, and partition tolerance. All 3 of those words mean something narrower than they sound like, and 2 of them mean something different from what they mean in the rest of computing. Consistency. In CAP, consistency means every read returns the most recent write, or an error. If I write a value, and you read a microsecond later on the other side of the world, you get my new value, not the old one. The formal name for this is linearizability. The system behaves as though there is one copy of the data, processing operations one at a time in real-time order, even though there are actually 3 copies in 3 cities. This is a much stronger promise than the C in ACID. That C means a transaction doesn't violate your database's rules. No negative balances, no orphaned foreign keys, same letter, unrelated idea. Availability. In CAP, availability means every request to a non-failing node gets a non-error response. Not fast, not correct, just an answer, rather than silence or a failure. Notice how weak that definition is. It says nothing about latency. A system that answers in 9 seconds is available under CAP. This is not what most people mean when they say a service is available, and that gap causes a lot of confusion. Partition tolerance. A partition is when messages between nodes are lost or delayed indefinitely. The network splits. Each side is still running, still healthy, still serving users. It just can't talk to the other side. Partition tolerance means the system continues to operate despite that happening. Those are the 3. The theorem says you can have at most 2. The pick 2 of 3 framing is the most widely repeated thing about CAP, and it's the least useful. It's a formatting artifact of the original slide. Here's the problem with it. Consistency and availability are properties you design for. Partition tolerance is not a property you choose. It's a description of the network you're running on. Networks partition. Fiber gets cut, a switch reboots, a misconfigured firewall rule drops traffic in one direction only. A garbage collection pause makes a healthy node look dead for 8 seconds. A BGP change removes a route. You cannot decide that this won't happen. You can only decide what your system does when it does. So the real statement is narrower and more useful than pick 2. When a partition occurs, you must choose between consistency and availability. That's it. That's the theorem. When the network is healthy, you get both. And CAP has nothing to say about your system at all. Let's walk through why the choice is actually forced, because it isn't obvious that there's no clever third option. 2 nodes, both holding a bank balance of 100. The link between them breaks. The user on the left writes a new value. Balance is now 50. Node A tries to tell node B, the message doesn't arrive. Node A has no way to distinguish B is unreachable from B is dead from my message got through and B's acknowledgement got lost. Now the user on the right asks node B for the balance. Node B has exactly 2 options. Option 1, answer with 100. The user gets a response, so the system stayed available. The response was wrong, so the system was not consistent. Option 2, refuse to answer. Node B knows it might be stale and won't guess. Nobody reads incorrect data, so consistency holds. That user got no service, so availability doesn't. There is no third door. Node B cannot learn the truth because learning the truth requires a message crossing a network that is currently not delivering messages. That's the proof, informally. Gilbert and Lynch published the formal version in 2002, and the core of it is that simple. Correctness requires information. Information requires communication, and a partition is the absence of communication. Eric Brewer presented this as a conjecture in a keynote at the PODC conference in July 2000. He'd been building large systems at Inktomi, which ran search infrastructure for a good chunk of the early web, and the trade-off was something practitioners kept running into without a name for it. It was a conjecture, not a theorem. He didn't prove it. 2 years later, Seth Gilbert and Nancy Lynch at MIT formalized it and proved it, which is what turned it into CAP theorem. Their proof works in the asynchronous network model. No shared clock, no bound on how long a message can take. That last detail matters. In their model, a node can never conclude that a message will never arrive because there's no upper bound on delivery time. Slow and never look identical from the inside. They also proved a weaker, more practical variant for partially synchronous networks, where you do have clocks and can use timeouts. In that model, you can build something that returns correct data when the network is healthy and stops answering when it isn't, which is what most real consensus systems do. In 2012, Brewer wrote a follow-up called CAP 12 years later, in which he said fairly directly that the 2 of 3 framing had been misleading and that the goal should have been maximizing consistency and availability under normal operation, then handling partitions deliberately when they happen. CP, consistency over availability during a partition. Most systems in this category use a quorum. With 5 nodes, a write needs 3 to acknowledge it. If the network splits 3-2, the side with 3 can still form a majority and keeps operating. The side with 2 knows it's in the minority and stops serving. This is what etcd does, and Consul and Zookeeper and HBase and by default MongoDB and Kafka. They're built on consensus protocols, Raft or Paxos or something in that family, and consensus is precisely a mechanism for refusing to proceed without a majority. The user visible behavior during a partition is that some requests fail or hang or get redirected. From a monitoring dashboard, a CP system under partition looks like a partial outage. That's the correct behavior. It's what you want for a system that stores who has permission to do what, or which node is currently the leader, or how much money is in an account. AP, availability over consistency during a partition. Both sides keep taking reads and writes, neither side blocks, every user gets served. The cost is that the 2 sides now disagree, and when the partition heals, something has to decide which value wins. The blunt approach is, last write wins, compare timestamps, keep the newer one, discard the other. Simple. And it silently destroys data. The discarded write was a real thing a user did. The more careful approach is to keep both and use version metadata. Vector clocks are similar, to detect that they're genuine conflicting siblings rather than one being newer. Then hand the conflict to the application to resolve. Amazon's Dino paper in 2007 is the reference point for this design, and their canonical example is the shopping cart. Merging 2 versions of a cart by taking the union of the items is almost always the right answer. A user might see a removed item come back. That's a minor annoyance. Refusing to let anyone add to a cart during a network problem is a much larger business problem. Cassandra, React, and CouchDB sit here. So does DNS. So does most CDN behavior. So does any system that describes itself as eventually consistent. The third combination gets listed in a lot of diagrams, and it's the one that doesn't survive contact with reality. A CA system is consistent and available and does not tolerate partitions. Since partitions are something the network does to you rather than something you opt into, the honest reading of CA is, this split has no defined behavior when the network splits. Single node databases get filed under CA, and that's a category error. A single node has no network between replicas, so there's nothing to partition. CAP isn't describing it. A traditional replicated relational database with synchronous replication is usually CP. When a replica becomes unreachable, the primary either blocks or drops it. Either way, somebody loses availability. If a system claims CA, the useful question is what it actually does during a partition. The answer is always either stops serving or serves possibly wrong data, which places it in CP or AP regardless of the marketing. CAP is narrow. It's worth knowing exactly how narrow because it gets applied to decisions it has nothing to do with. It's binary about consistency. CAP-C is linearizability, the strongest form. Real systems live on a spectrum. Causal consistency, read your writes, monotonic reads, bounded staleness, snapshot isolation. A system can be non-linearizable and still make useful guarantees. CAP collapses all of that into one bit. It's binary about availability. Under CAP, a system that responds is available. Latency doesn't enter into it. In practice, latency is the thing users experience, and responded in 4 seconds and returned an error often feel identical to them. It only describes partitions. CAP says nothing about what your system does the other 99-point-something% of the time, which is where almost all your engineering effort goes. That last gap is the one Daniel Abadi addressed in 2010 with an extension called PACELC. It reads, if there is a partition, choose between availability and consistency, else choose between latency and consistency. The second half is the addition, and it's the half that describes daily operation. Even with a perfectly healthy network, keeping replicas in agreement costs round trips. If a write has to reach a majority across 3 regions before it's acknowledged, that write is bounded by the speed of light and the routing between those regions. Every millisecond of consistency is paid for in latency. So Cassandra is described as PA/EL. During a partition, it favors availability, and in normal operation, it favors latency. A system using synchronous majority replication is PC/EC. It gives up availability during a partition, and it accepts the latency cost the rest of the time. PACELC covers the trade-off you make every day, rather than the one you make during an incident. In practice, CAP is rarely a decision made once for a whole architecture. It's made per piece of data. Financial transactions, inventory counts for something scarce, unique username registration, leader election, distributed locks, these want CP. Being wrong is more expensive than being unavailable. User sessions, activity feeds, view counters, recommendations, cached product listings, presence indicators, these want AP. Serving a slightly stale number is cheaper than serving nothing. The same company runs both, usually in the same request path. A product page might read the description from an eventually consistent cache and the remaining stock number from a strongly consistent store in one page load. Modern databases increasingly make this a per operation setting than a per system one. Cassandra lets you specify a consistency level for individual queries, one quorum all. So the same cluster is AP for one query and effectively CP for the next. DynamoDB has eventually consistent and strongly consistent reads, priced differently. Cosmos DB exposes 5 distinct consistency levels. The choice moved from architecture diagrams down into the query. To restate the whole thing in its most useful form, partitions are not optional. Your network will split and you don't get a vote. When it splits, a node that can't reach its peers has to either answer with data it can't verify or refuse to answer. Those are the only 2 moves available to it. Which one you pick is a property of the data, not your taste. And it's a decision you're making whether or not you make it deliberately.